Oh hey! In today's video, I'm gonna introduce to you the two-way ANOVA or factorial analysis. We will discuss the different aspects of a two-way ANOVA and calculate it by hand to interpreting results. Now imagine I gave an arithmetic test to boys and girls of different age groups, 10-year-olds, 11-year-olds, and 12-year-olds. And now I have a list of their scores. And I want to determine what impacts the variation. Is it gender? Is it age group? Or is it both gender and age group? So I have two factors, gender and age. That's why it's called a two-way ANOVA. Now let us compare a one-way ANOVA to a two-way ANOVA so we can have a better understanding. Let me call my assistant, Toy Nuts, to explain it to you. Wait, what the? Hey, Toy Nuts, explain to them how complicated a two-way ANOVA compared to the previous topic, which is the one-way ANOVA. Yes, sir. Whatever. If we are to analyze one-way ANOVA with the same data, let's say we take score variation by age. Let's have the 10-year-old group, 11-year-old group, and 12-year-old group. Let's take the average of 10-year-old group, 11-year-old group, and 12-year-old group. And also let's look at it as one big large group and take the average, which is equal to 9. Then I will take all the averages and form a table of averages. So I end up with one row and it's all average by age. Now in a two-way ANOVA, it's different. It's more complicated. Just imagine, I want to analyze this data by age and by gender. Now, let's put back our data of 10-year-olds, 11-year-olds, and 12-year-olds. Now, I have everything the way I like it. So, I have above the first group of data, let's label it boys, and the bottom group is girls. I'll take the average score for each age group for the boys, then take the average score of all the boys, and it's 7.7. Now let's do the same exact thing for the girls. Get the average for each age group. Then, the total average for all the girls, which is 10.3. Now let us put it all back into a single table and call it the mean table. Let us end up with 3 rows of data, boys, girls, and the average row. We also have 4 columns of data, the 10-year-olds, 11-year-old data, 12-year-old data, and the average data. In this table, I ended up with averages for all the boys by age group and total. Also, averages for all the girls by age group and total. I have 10-year-old data broken down by gender and total average, 11-year-old broken down, and 12-year-old broken down. Having data organized in a table like this makes it easier to calculate degrees of freedom, understand the factors, and calculation we have to make later. Our first factor is gender, second factor is age, and it doesn't make a difference if we swap these factors. A two-way ANOVA is a lot more complicated than a one-way ANOVA. In fact, if I will put back our table for one-way ANOVA back in, we could see that the average for two-way ANOVA is already the entire table for the one-way ANOVA. In a one-way ANOVA, given this data, I want to work with 4 averages. While in a two-way ANOVA, I have 12 different averages. Having data organized in this table makes it easy to work with and a lot easy to understand. In that sense, what we're doing with two-way ANOVA is that we're taking our data and reorganize it in a lot of different ways and analyze it. We organize it based upon age group to calculate sums of squares of my first factor, which is age. Then, reorganize the data, this time by gender. This time, I have a thing called sum of squares for the second factor, which is gender. Then, analyze based upon gender. And finally, let's take all the data into one big chunk and let's call it total sum of squares, then analyze it as well. In the end, I have sum of squares for the first factor, which is gender, sum of squares for the second factor, which is age, sum of square for both factors, age and gender interaction, sum of squares within the error. If I add all this up, I get sum of squares total. Hey, Sir Puntilar, I'm done. It's your turn.
Thank you, Toy Nuts. Now let's use the same data and solve two-way ANOVA by hand.
Which factor affect the scores of 10 to 12-year-old boys and girls? Is it their gender? Is it their age group? Is it both? Or neither? In this case, we are going to use the default confidence level, which is the 95%. Now let's establish our hypothesis. The first null hypothesis, gender will have no significant effects on pupil score. Second null hypothesis is age will have no significant effect on pupil score. And third null hypothesis is gender and age interaction will have no significant effects on pupil score. Now, through ANOVA, we will attempt to disprove the null hypothesis by stating our alternative hypothesis. First, gender does have a significant effect on pupil score. Second, age has a significant effect on pupil score. And third, gender and age interaction has a significant effect on pupil score. So, given an arithmetic test to boys and girls of different ages, boys and girls 10-year-olds, boys and girls 11-year-olds, and boys and girls that are 12-year-olds. And in the middle is their scores. I wanna determine whether gender or age group or both impact the test scores. So I have two factors, gender and age. So let's organize the data. The first thing to do is organize it by boys and girls. Then, let's start with the boys' data. We have the 10-year-old boys and their test scores for the 11-year-old boys, and the test scores for the 12-year-old boys. Then, let's move that right there. Now, let's do the same exact thing to the girls. Like the boys, let's have 3 columns of data. 10-year-olds and their scores, 11-year-olds and their scores, then finally, 12-year-olds and their scores. So now, let's build the third table, the mean table. In this table, let's have 3 columns of data by age group and 2 rows by gender, boys and girls. The boys and girls is the first factor, which is gender. The second factor is the age group. So let us calculate the mean or average for the 10-year-old boys, and that is 6. Let's plot it to the mean table. 11-year-old boys is 7. Bring it to the mean table. The mean test score for 12-year-old boys is 10. Now, let us take the average of all the boys. And the average test score for all the boys is 7.7. Now, let's do the same thing for the girls. Take the average test score for 10-year-olds, which is 7. The average test score for 11-year-old, which is 10. Then the average test scores for 12-year-olds, which is 14. So, the average for all the girls turns out to be 10.3. The average test scores for all the 10-year-old boys and girls is 6.5. The average test score for all the 11-year-olds is 8.5. And the average test scores for all 12-year-olds is 12. And the average test scores for all the children turns out to be 9. Now, let us calculate a lot of sum of squares. Sum of squares for the first factor, which is gender. Sum of squares for the second factor, which is age. Sum of squares within, which is error. Sum of squares between both factors. If we add all this up, it's gonna be equal to the sum of squares total. I'm actually gonna calculate the sum of squares with the check marks. Then, let's determine sum of squares for the both factors algebraically. First is sum of squares for first factor, which is gender. So let us bring back our tables in and calculate the sum of squares for the gender. We use the boys' average against the boys' table and the girls' average against the girls' table. And then, let's take the grand total average against both of them. First, let's work with the boys' data. Let's organize the boys' score and organize it into a single column. Then, let's use the boys' mean all the way to all the scores. Then, subtract 9, which is the grand total average from each of these values. So, 7.7 minus 9 is equal to negative 1.3. Then, square that, and that is equal to 1.7. So, since they are all the same, let's just do the same all the way down. Then, let us sum this up, and that is equal to 15.3. I'm gonna do the exact same thing to the girls' score. Take all the data and organize into a single column. Then, copy 10.3 next to the scores. And subtract the grand mean, which is 9 by the way, and this is equal to 1.3. Square it, and that is equal to 1.7. Then, let's do that to each girl's score. Then I'll sum them up. The sum of squares is also equal to 15.3. So the sum of square for the first factor is gonna be equal to 15.3 plus 15.3, and that is 30.6. Now let's do the sum of squares for the second factor, which is age. Let's bring back our tables. Now I'm gonna take the average values for each of these columns from each of the age group, and I'm gonna compare it against the grand total mean. So I'll take the boys' data into one column again. Take note that I use a color coding for its age group. Red is for 10-year-olds, so it's 6.5. Blue is for 11-year-olds, so that is 8.5. And green is for 12 years old, and that is 12. So I'll take 9 and subtract to its average by age. So 6.5 minus 9 is negative 2.5. Square that and it will be 6.3. Let's do the same for this age group of 10-year-olds. Next, for the 11-year-olds, 8.5 minus 9 is negative 0.5. Square that and it will become 0.25. Do that to all 11-year-olds. Next is the 12-year-olds. So 12 minus 9 is equal to 3. Square 3, that is 9. Do that to the rest of the age group. Then, add everything up. This sums to 46.7. Now, I'll do the same for the girls' test scores. Organize the data into a single column. Then, I'll do the same since they are exactly the same with the boys. Then, of course, if we sum this up, the sum of squares is also 46.7. So, the sum of squares for second factor is 46.7 plus 46.7 equals 93.4. There we have it. Now for the sum of squares within, again, let's bring back our table. Let's take first the boys' data and organize it again into one column. Now let's take the boys' average test scores by age group and subtract to each test score by age. Remember that red is for 10-year-olds, blue is for 11-year-olds, and green is for 12-year-olds. So, 4 minus 6 is negative 2. Square it, the answer is 4. 6 minus 6 is 0. Square, still it's 0. 8 minus 6 is 2. Square, the result is 4. 6 minus 7 is negative 1. Square, it's 1. Next is the same, so we just copy. 9 minus 7 equals 2. Square, and it's 4. 8 minus 10 is negative 2. So, negative 2 times negative 2 is 4. 9 minus 10 is negative 1. Square, and it's 1. 13 minus 10 is 3. 3 times 3 is equal to 9. Then, sum them up. The sum of square is 28. Now, let's repeat the same process for the girls. Let's just use the girls' average score by age group, then subtract. 4 minus 7 is negative 3. Negative 3 times negative 3 is 9. 8 minus 7 is 1. 1 times 1 is 1. 9 minus 7 is 2. Square, 2 times 2 is 4. 7 minus 10 is negative 3. Square, the answer is 9. 10 minus 10 is 0. So 0 times 0 is 0. 13 minus 10 is 3. Square 3 and it will be 9. 12 minus 14 is negative 2. Square, then it will be 4. 14 minus 14 is 0. It doesn't matter. The result is still 0. 16 minus 14 is 2. Square it. The answer is 4. Then, sum it all up. The sum of squares for the girls is 40. Now, the total sum of squares within or error is 28 plus 40, and that is 68. And there we have our sum of squares within. Now, let's have the sum of squares total. Again, let's bring back our tables. This time, let's take all the test scores and compare it against the grand mean, which is 9. Now, let us make one big column of all the test scores. Then, we subtract the grand mean from each of the test scores. Four minus 9 equals negative 5. Square equals 25. 6 minus 9 equals negative 3. Square it equals 9. 8 minus 9 equals negative 1. Square it. It is 1. 6 minus 9 is negative 3. Square. Then it's 9. Another 6 minus 9. So just copy from the previous. 9 minus 9 is 0. Square it. Still 0. 8 minus 9 is negative 1. Square and still it's 1. 9 minus 9 is 0. That is all the way. 13 minus 9 is 4. So 4 times 4 is 16. 4 minus 9 is negative 5. Negative 5 times negative 5 is 25. 8 minus 9 is negative 1. So square, negative 1 times negative 1 is 1. 9 minus 9, again, it's 0 all the way. 7 minus 9 is negative 2. Square it. Negative 2 times negative 2, that is equals to 4. 10 minus 9 is 1. Square, the result is 1. 13 minus 9 is 4. Square it. 16. 12 minus 9 is 3. Square it. Then it's 9. 14 minus 9 is 5. Square it. 5 times 5 is 25. 16 minus 9 is 7. Square it. So that is 7 times 7 equals 49. Sum them up and we have 200 as our sum of squares total. So there we have it. Now, only the sum of squares for both factors is left. So, using algebra, we can easily get the value for this. It's actually the difference of the value of sum of squares total, which is 200, and the sum of the other sum of squares. like this. So, 200 minus 30.6 plus 93.4 plus 68. So, if we are going to simplify this, we get the sum of squares for the both factors. And the answer is 8. Now, there we have the sum of squares for both factors. Now, we're ready to plot the ANOVA table. Now, let's take a look once again with our 3 null hypotheses before we start the ANOVA table. Now, let's start. After a long preparation in solving for the sum of squares, that was a lot of sum of squares. Let's plot them to our ANOVA table. Now, let's calculate the degrees of freedom, or the DF. Let's bring back our mean table. To calculate the degrees of freedom, or the DF, for the first factor, which is gender. For the DF, just take the number of rows minus 1. So we have boys and girls. So we have 2 rows. So it's 2 minus 1. And of course, that is equals to, the last time I checked, is 1. So the degrees of freedom for the first factor is, of course, 1. For the second factor, which is age, let's take the number of columns minus 1. So I have 3 columns. So 3 minus 1 is equals to 2. The degrees of freedom for the second factor is, of course, 2. Now, let's calculate the degrees of freedom for the sum of squares within. Let's bring back these tables and take the number of observation for each age group. So, n minus 1, which is 3 minus 1, and that is equals to 2. Then, I'll do that for each age group because they all have 3 as the number of observation. Then, we add all up 2 plus 2 plus 2 plus 2 plus 2 plus 2. That is equals to 12. So, we have 12 as the DF of sum of squares within. Now, for the DF, or the degrees of freedom for the sum of squares for both factors, it's actually the product of the DFs of the sum of squares for the first factor and the sum of squares for the second factor. And that is 1 and 2. So 1 times 2 is 2. The degrees of freedom for both factors is 2. Now, sum them up and boom! We have the DF of the sum of squares total, and that is 17. Now, let's calculate the mean square as well as the F ratio, or the F score, and how we interpret those results. Right here between the green region and the red region is our critical value, which we will get from the table later. If the F score will fall into the rejection region, or in the right of the critical value, the red part, we reject the null hypothesis. But if the F score will fall on the left of the critical value, or the green part, then we fail to reject the null hypothesis. Now, let's start with the first factor, which is gender. The mean square is actually the sum of square divided by its degree of freedom. And that is 30.6 divided by 1. And of course, that will be equals to 30.6. For the sum of squares within, we have 68 divided by 12 equals 5.67. Now, let's calculate the F score to see if we reject or support our null hypothesis. Let's start again with the first factor, which is gender. So the F-score is mean square of the first factor divided by the mean square of the sum of squares within. And that is 30.6 divided by 5.67. And that is equals to 5.4. 30.6 is the numerator. So our degree of freedom of 1 is also called the degree of freedom for the numerator. Since the 5.67 is the denominator, its degree of freedom of 12 is the degree of freedom for the denominator. Now to write the result, let's have F distribution, F, open parenthesis, the degree of freedom of numerator, which is 1, comma, degree of freedom for the denominator, which is 12, close parenthesis, equals to 5.4, which is the F-score. Then I'll write P is less than 0.05 because we are going to test it using the 95% confidence level. Now let's bring up the table for the 95% confidence level. Across the top is the degrees of freedom for the numerator. And the number down the side is the degrees of freedom for the denominator. So now let's take 1 as our degrees of freedom for the numerator. Let's use this column of data. Then 12 as our degrees of freedom for the denominator. Across. And where they intersect is our critical value. And it's 4.75. Now let's bring back our F distribution. So any values greater than 4.75 or to its right, we will reject the null hypothesis. And 5.4 of course is greater than 4.75. So I'll reject the null hypothesis. Reject this statement. Gender will have no significant effect on student score. Now let's calculate for the F-score for the second factor, which is age. Again, the mean square is sum of square divided by the degrees of freedom. That is 93.4 divided by 2. And that is equal to 46.7. Now, let's calculate for the F-score. That is 46.7 divided by 5.67, which is the mean square of the sum of squares within. So, 46.7 divided by 5.67 is 8.24. Again, we will write F distribution. F, open parenthesis, 2, 12, close parenthesis, equals to 8.24, which is the F-score. And again, P is less than 0.05 because we'll bring back the 95% confidence level table to interpret our result. Let's take the DF for the numerator, which is 2, and use its column. Then, the DF for denominator, which is 12, and use its row. Their point of intersection is 3.89, and this is our critical value. Again, let's take a look to our F distribution. Our critical value is 3.89. The F-score is 8.24 and will fall somewhere here, and of course, it's greater than the critical value of 3.89. So, we reject the null hypothesis, which is age will have no significant effect on student score. Next up is sum of squares for both factors. So, 8 divided by 2, that is equals to 4. The F-score is 4 divided by 5.67, and that is equals to 0.71. Now we write F distribution, F2, which is the DF for numerator, comma, 12, the DF for the denominator. equals 0.71, which is the F score. Then P is less than 0.05. Let's bring back our 95% confidence table. We have our DF for numerator, which is 2, and DF for denominator, which is 12. So the critical value is the same as the previous one, which is 3.89. Now the F score is 0.71, and that is of course less than our critical value of 3.89. So it will fall somewhere here in the green region. In this case, since the F score is less than the critical value, or it is in its left part, therefore we fail to reject the null hypothesis. So it means that gender and age interaction will have no significant effect on pupil's score. So we reject the first two null hypotheses that includes the impact of gender and age, but we fail to reject the last one, the interaction of age and gender. So gender will have no significant effect on student score. Well, it's rejected. Gender does have a significant effect on student score. The next hypothesis is rejected, which is age will have no significant effect on student scores because age, based on the data, has a significant effect on student score. And the last hypothesis, gender and age interaction, will have no significant effect on student score. We failed to reject that, and we could kind of conclude that probably it's a true statement.
So, that's all with this video lesson or tutorial about two-way ANOVA. Thank you, Doc Marian Sarmiento, for the opportunity and challenge to have this topic. Hey, Toy Nuts, it's time to say goodbye.
Yeah, whatever. Bye, friends.